Hey there, physics fans. Today we're going to talk about a couple of problems where we have to apply both conservation of energy and conservation of momentum in order to solve them. Now, some of these are going to require angular momentum and some of them will require linear momentum, but that's perfectly fine. It's still conservation of momentum. Each one of these problems cannot be solved on its own by either conservation of energy or conservation of momentum. Instead, we need to develop a strategy that identifies which portion of the problem falls into which category. So I'm going to go through each of these demos and walk you through a strategy and how you'd be able to solve it. So let's go ahead and dive into our first one. The first problem we're going to talk about is where the cart is sliding along a frictionless track and collides with a ball that's hanging by a string like a pendulum. We're tasked to find the maximum height the ball reaches following the collision. Now recall from conservation of momentum, anytime we have a closed and isolated system that undergoes an explosion or a collision, we can apply conservation of momentum. So in this case, it's going to be one-dimensional. We're going to know the velocity of the cart immediately before the collision and after the collision, and we're going to assume that we can determine the velocity of the ball immediately after the collision, and it's also going to be along the x-axis. From there, we can move into a conservation of energy problem, where we set the potential energy of the ball, UG equal to 0, at the bottom of the arc, and we now take the velocity immediately following the collision and say that is the speed at this point. Then, once the ball reaches the top of the arc, we can determine that all of the kinetic energy has been transferred into gravitational potential energy. With that, and the assumption that the work due to non-conserved force is equal to 0, we can finally solve this problem. So let's go ahead and talk about our second problem. In this problem, we're going to have a ball that rolls down a ramp that is on a frictionless surface. The ball is going to start from rest at an elevated position where it has gravitational potential energy, and it will roll down until a position where we set the gravitational potential energy equal to 0. At this point, all of the gravitational potential energy in the system has been converted into both rotational and translational energy of the ball. Once the ball reaches the end of the ramp, the system is going to undergo an explosion where the ball leaves the ramp in one direction and the ramp continues to move in the opposite direction. At this point, we'll apply conservation of linear momentum, where we took the speed of the translational speed of the ball, and that is now the velocity of the ball immediately after the collision. And finally, we'll be able to solve for the velocity of the cart system going in the opposite direction. All right. So let's go ahead and move on to our next problem. For this problem, we'll be applying conservation of energy and conservation of angular momentum. In front of me, I have a rotating platform that has a projectile launcher mounted on top of it. The projectile launcher will use a spring to launch a projectile out of the barrel. I can use conservation of energy in order to determine the speed of the projectile as it leaves the barrel. And then I can model my system using conservation of angular momentum, undergoing an explosion, where I use the initial speed of the ball to determine what its angular momentum is as a point mass moving in a straight line about an axis of rotation. And I use the information that I know about the rotating platform as well in order to determine the angular speed of the platform immediately after my explosion. Okay, let's talk about our next demo. This next problem is very similar to our rotating platform problem. Again, we have a projectile launcher which uses a spring to launch the ball out of the barrel. So we can use conservation of energy in order to determine the speed of the ball immediately upon exiting the barrel. We then use that speed and say is the velocity of the ball immediately before a collision with a cart. Now the ball and the cart go through a completely inelastic collision and then continue off in the same direction that the center of mass of the system was already moving. For our final problem, we're going to look at a Galileo cannon. This is where we have a multiple ball system that falls from some elevation and strikes the ground. Upon striking the ground, the uppermost ball is launched to a much higher elevation than it would have been if dropped on its own. In order to first solve this problem, we'll use conservation of energy. Setting the gravitational potential energy equal to 0 at the ground, we'll model our initial position at an elevation where we have nothing but gravitational potential energy, and we'll determine the speed of the system immediately before striking the ground. We'll use that speed and have it be our velocity just before a collision and apply conservation of linear momentum in order to determine the velocity of the ball immediately after the collision. There you have it, physics fans.